What is lazy binding? Before we can answer this question, we need to first understand what is linking process and what does a linker do in an operating system. At compile time, build time, or load time, linker resolves all those references to symbols an application or a library needs, and that is linking. You might ask, what are these external references? Now, external references are all those functions or global variables an application developer or a programmer uses from external sources or external libraries into the code of the application or the library he is developing. There's one powerful feature or an idea which makes this whole process of linking or linker's job superior is lazy binding. And in this video, we will try to understand this concept. When you run a program that links to a shared library, the program needs to know where to find the functions defined in that library. An application would usually have many of those functions, and maybe even hundreds or thousands of those functions. But what if the program only gets to use some of those functions in a particular run? You might ask why. The answer is that every run, a program or a library does not execute all the code it has. It just executes a small portion of it, especially the portion which is in the hot path. You might ask, what is a hot path? Now, hot path is the most frequent path taken by a computer in a code or a program while it is executing. In many cases, that portion is very small compared to the whole code. Code which application has is usually quite enormous. And that's why it would be wasteful to load all the code and libraries into memory just to access a few functions. And hence it's very useful to just selectively resolve only those external functions which are needed at runtime. Now here is when lazy binding comes into play. Instead of loading the entire set of libraries into memory, the dynamic linker only loads the subset of library that is actually needed at runtime. And even better, it only resolves the function calls when they are actually made. The dynamic linker thus avoids us hundreds or thousands of unnecessary relocations at load time. Wait, you might ask, what are these relocations? Relocation is the process of resolving the external reference by a linker. Every external reference, of course, needs to be resolved. But as I said, if we are anyway going to use only few of those external references, there is really no point in resolving all of those. And that's where lazy binding comes into play. It saves us resources, it saves us time, and it saves us many relocations. So how does a linking process takes care of this? How is it implemented? On most of the systems, or at least Linux kernel-based operating systems, it uses two data structures. One is called global offset table or GOT, and the second is procedure linkage table or PLT. In this video, we would try to limit ourselves to Linux kernel-based operating systems, but similar concepts would apply even on Windows and Mac OS. We'll keep ourselves glued to Linux kernel to keep this video short. On most modern Linux distributions, every time you compile a binary which uses external functions, it would have a PLT or a GOT table. Not all external references are resolved at compile time, so all the binaries usually have a framework built into them so that they could resolve these external references later at load time or runtime. Let's try to understand this framework so that we could easily understand the lazy binding later. Now picture this. You have got a procedure linkage table or PLT sitting inside your code segment in your binary. Note this is well before external references are resolved. Each entry in the table contains a set of instructions in assembly language. Now, if your binary needs to use external functions, each external reference would have an entry in the PLT table. At the start of the PLT table, there are few reserved entries, and one of them actually is saved especially for dynamic linker. You might ask, what is this spatial entry? We would talk more about it in a bit. There is another useful table here for dynamic linker, and it's called global offset table or GOT. Like PLT table, this table also has few reserved entries for dynamic linker. This table also has one entry for each externally referenced symbol, but there are actually few differences between GOT and PLT. You see, each entry in GOT has an address stored in it, and during load and execution time, these addresses are updated to new addresses. Every time there is a call to external function, GOT entry for that function is updated from its initial value. Initially, it is always pointed towards a related PLT entry for that very function. But at some stage, if the corresponding function gets a call from the application or a library, entry in GOT is updated to a location in the external library where the actual definition of that reference was, and all this takes place in virtual address space of the process. GOT is thus placed in writable section usually. Compare this to PLT table, which is kept in an segment which is part of the code, and it has usually just read-only and execution permissions. Main reason for that is that GOT addresses get updated during the load or runtime of a application. PLT table, on the other hand, has just code inside it and can be in a read only, and it just needs executable permission for execution. Let's dig in more detail. In this visual representation, we have an orange rectangle symbolizing an application binary or a process loaded in memory. The procedure linkage table is located within the code segment of virtual address space. The top few elements are designated for dynamic linker. Meanwhile, at the bottom, you can see we have global offset table, which also reserves some entries for dynamic linker. Keep in mind that every external reference or a call to a function defined outside the application will have a corresponding entry in the PLT or GOT table. Now let's delve deeper into these tables. We'll extract the PLT table from the orange rectangle, and let's draw a new diagram on the left side to clarify its structure. Here the PLT table resides in the code segment of the application, and as mentioned earlier, the first entry is reserved for the dynamic linker. All PLT entries usually have some assembly instruction in them. A simplified set of instructions could be a jump instruction at the top, followed by few instructions which help dynamic linker resolve those unresolved external references. Let's revisit the original diagram from earlier and extract GOT table for a closer examination. As the GOT table addresses are writable, they find their home in the data segment in the binary. The GOT table is usually initialized with addresses during the compilation process. Let's enhance this GOT table in the diagram with some more realistic data to make it more clear. If you observe the first three rows, which are exclusively reserved for dynamic linker, these entries play a crucial role in loading the dynamic linker. The fourth index here holds our function fun, which we use later for examination and discuss an example. The initial value here points to the second entry in PLT entry for the same function fun. The significance of this will become soon more clear. Keep in mind an essential aspect of dynamic linker's functionality. Once it resolves an external function or a call, it updates the address entry for that function in GOT table. It directs it directly to the actual memory location of the function, and this saves dynamic linker from resolving the same function again for future calls. Now that we have expanded our tables, let's bring them together to form a virtual address space of a running application. Picture this layout. On the left side, we have a loaded application in memory, complete with both data and code segments. The PLT table resides within the code segment while the GOT table is nested inside the data segment. Additionally, there's a bit of a code in the code section that calls the function fun we just talked about. As we have previously mentioned, the function fun has corresponding entries in both PLT and GOT tables. Every time an external function call is made in a running program, such as when we call function fun, the execution leaps to a PLT entry for that function. The first instruction in the PLT entry is a jump instruction, which actually propels us to the location stored in the GOT entry for that function. What that essentially means is that the jump instruction actually uses GOT entry location to jump. As you know, the initial value actually points to the second instruction in the PLT entry. So this jump ultimately leads to the second instruction in the PLT entry. The remaining two entries initiate a call to dynamic linker to resolve this function. The dynamic linker then leaps into action. It loads the library, calls the function, saves the location for future use, and updates the GOT table to ensure that future calls to the same function don't require resolution again. Let's delve deeper into the process. On the left side, we have a program or a process loaded into memory and ready for execution. An external function called to fun leads directly into its PLT table entry. As expected, the first instruction invokes a jump, a leap into address stored in GOT table for that very function. Initially, the address, as we discussed already, points to second instruction in the PLT table entry itself, which proves beneficial when invoking the dynamic linker for the first time. Now, dynamic linker springs into action, locating and loading the library into memory. And following this, in the fourth step, the function execution concludes and the return value is dispatched back to the caller. Simultaneously, the dynamic linker updates the GOT entry for the same function, ensuring it points directly to the address of the function in loaded memory. This streamlined process allows for a more efficient calls and smoother execution of the program in future. From this point forward, all successive calls effortlessly leap straight to the function within the library and returns. It effectively bypasses the costly step of loading the library and relocating the function call. So what are the advantages of lazy binding? First up would be reduced startup time. With lazy binding, a program only loads and links the functions or symbols it needs only when they are actually in use. That means faster startup times and less time wasted on unnecessary tasks. Imagine launching your program in the blink of an eye. That's the power of lazy binding. Next would be reduce memory usage. By only loading the functions or symbols that are actually needed, lazy binding helps your program use less memory. That means more space for your program to run other programs. And of course, less chance of other programs crashing due to lack of memory. And last but not least, it also results in improved performance. So you will have a better seamless user experience. Lazy binding may seem like a silver bullet for optimizing program performance and resource usage, but let's not forget the potential downside. Here are some of the situations in which lazy binding may not be appropriate. First up, security concerns. Lazy binding can introduce security vulnerabilities due to software bugs. For example, a program loads and links code from untrusted sources. If a malicious actor is able to substitute their code for a legitimate library, lazy binding can allow that code to be executed undetected. Next problem would be, for example, initialization overhead. While lazy binding can help reduce startup time and memory usage, it can also introduce additional overhead at a later stage when finally program needs to load and link the necessary symbols and functions it deferred earlier. In some cases, this overhead may not be acceptable at all, especially in real-time and high-performance systems where every millisecond counts. Third, and one of the important problems with lazy binding is resource constraints and the undeterministic behavior it results in. In environments with very limited resources or limited memory processing power, such as embedded systems, the overhead associated with lazy binding may be too high. It's like trying to fit a square peg in a round hole. Sometimes it just doesn't work. What I mean here is that it might lead to the lazy binding might lead to undeterministic behavior. Lazy binding, for example, can make programs behave more unpredictably since the order in which symbols or functions are loaded and linked can vary depending on how the program is used. In situations where deterministic behavior is critical, like lazy binding may not be appropriate at all. Let's go back to the terminal. We have our main function with few printf calls. It would become soon clear what print at the rate PLT means. Let's list down all the dynamic relocations dynamic linker must resolve before or during execution of application. By default, modern Linux operating systems have lazy binding enabled. So every application would have a PLT section to which all calls to external functions would go first. You can imagine that every call you make in your code to external function is placed in a new function which is just a wrapper and calls that external function on your behalf. This wrapper function is placed in PLT table entry for that function. So in this code, all calls to printf eventually go to an entry in PLT table. This can be clearly seen in the disassembled code of PLT section. In every PLT section, we have 3 instructions in total. First one is a jump to global offset table entry for that function. As soon as program reaches to the printf function, it jumps to the PLT entry. From the PLT entry, the first location jumps to the GOT location. We can demonstrate this via GDB session of the application. Let's put a breakpoint at main function. After disassembling main function, you can see we are just waiting before printf function call. Let's disassemble the PLT entry to which this call instruction jumps to. The first instruction of PLT entry has a jump instruction. This jump instruction reads an entry from GOT table and uses the stored value as destination for jump. Look at the address value. Let's see what that location is. Printing the GOT entry for the address, it seems the location is the next instruction in PLT itself. We can check with GDB session that the address value inside GOT has indeed been changed. This would make sure that next time printf is called, first jump instruction in the PLT entry would take us to printf location directly without doing a dance between PLT and GOT. We can validate this by disassembling the new address in GOT. It indeed looks like printf function from library. The overhead of new calls is very low now. This is how lazy binding works. With this, we conclude this session about lazy binding. Thank you.